I want to welcome you to another statistical party, because I'm going to call this party. Today, the focus is basically going to be on variance of logistic regression part 2. Okay, you remember yesterday I walked you through the variance of logistic regression part 1. We focus on the multinomial logistic regression and the ordinal logistic regression, but today the focus is going to be on beta regression. Okay, so I'm going to go to the outline. In the outline, four of us want to have a quick review on logistic and its variants. Then from there, I'm going to move into beta regression. Okay, so I think I'm going to start my recap from linear regression. You know, uh, if you look at what we've been doing, I've walked you through different kind of regression type model. Okay, I started from linear regression model. From linear regression, we went into logistic regression, what I call the binary logistic. From binary logistic to multinomial, from multinomial to ordinal, and from ordinal now to beta regression. And let me tell you, in all of that, we are actually trying to characterize relationship among variables. Okay, we use linear regression in a situation where the response variable is continuous. Okay, we use linear regression in a situation where the response variable, I mean, the dependent variable is continuous. When the response variable is no longer continuous, but is categorical in such a way that it has two levels, we're going to use binary logistic. Now, when the levels of the categorical response is more than 2 and they are not ordered, we're basically going to use multinomial logistic regression. So what if they are ordered? If they are ordered, we're going to use ordinal logistic regression. Okay, let me tell you what actually determine the type of regression that we basically going to fit depends on the nature of the response variable. I'm going to say that again. So what determine the regression type model that we basically going to fit depends on the nature of the dependent variable that we also call the response variable or the outcome variable. So I'm going to repeat myself again. When I'm seeking to characterize relationship between variables and the nature of the response is continuous, we're basically going to use linear regression model provided other assumptions hold. When the nature of the response is no longer continuous but categorical in such a way that there are two possible outcomes, we're basically going to use binary logistic regression. But situation where the nature of the response is more than 2, but they are not ordered, you got more than 2 levels, but they are not ordered, okay, like race, okay, and stuff like that, we're basically going to use multinomial logistic regression. But situation where the level of the response is more than 2 and they are ordered, we're going to use ordinal logistic regression. Okay, today, what of in a situation where the response variable is actually rate, proportion, okay, percentage, okay, then we can no longer use other form of logistic regression model. When you make use of them, you're basically going to mislead. We're going to use what we call a beta regression model. Because in statistics, we have a distribution in statistical theory that we actually call beta distribution. And this beta distribution, settle in, model a random variable that is in the range of 0, 1. When I say 0, 1, I'm talking about you having this x greater than 0 but less than 1. It is not just like 0, 1, 0, 1 in case of binary logistic. No, it is a fraction. It's going to know something between 0 and 1 is going to be a rate, a proportion, or a percentage. So imagine you want to make, you want to actually explain an unemployment rate, okay? Inflation rate, okay? You're basically going to consider beta regression. Okay, so I want to walk you through beta distribution now because you know why? When I'm talking about linear regression, the probability distribution of the response variable is normal. I'm going to say that again. When I'm working with the linear regression, where the nature of the response variable is continuous, the underlying distribution of the outcome variable is normal. When I walk you through binomial, like walking you through the binary logistic, the underlying distribution of the response variable is binomial. And that was why we're specifying family equal to binomial when you want to run logistic regression in R. Okay, now that we are now focusing on a beta regression, then the underlying distribution is basically going to be a beta distribution. So what I want to display now is to four of us walk you through the property of the underlying distribution for the beta regression that we call beta distribution. Now, if you take a look at what I'm displaying now, I'm actually displaying the how flexible the beta distribution is when we vary the numbers of parameters, as you can see. So this is a probability density function. But before I show you all of that, I need to show you the statistical architecture of a beta distribution. Okay, the beta distribution is defined as what you're seeing now. We have f of y, the p and q are the parameters of the beta distribution. They represent shape parameters. Shape. Okay, p and q. Okay, the p and q that you are seeing, okay, they represent shape parameters. And that is what make the distribution to be more flexible. It's one of the most flexible distribution in statistics. Because of its flexibility, it can be used to model, most of, some of real life practical situation, provided it's actually the range of the random variable is between 0 and 1. Because we needed a more flexible model to be able to capture a random variable that takes a value between 0 and 1. The distribution had to be more flexible. Okay, so take a look at that. The state space of y, okay, 0 less than y less than 1. Take a look at all of that, okay? And, this distribution can be reparameterized if we want to use it in modeling, like, want to use it in a situation whereby we basically believe the response variable is related to some predictors. Because of that, Ferrari, okay, and Cribari Nero 2004 proposed having a different parameterization. Okay, the parameterization is just like, okay, the mean is going to be P over P plus Q. Let me tell you, when Y follow a beta distribution, the mean is going to be P over P plus Q. Okay, then phi equal to P plus Q. Okay, now I want you to see the second model now. Okay, when you take a look, I'm going to use my point. Give me 1 second. I'm actually going to use my pointer right now. So I'm talking about this guy now. Okay, you can see this guy now. Okay, they are able, the Ferrari and 2004, they actually reparameterize the conventional beta regression. I mean, sorry, the beta distribution. Okay, they just plug in, mu to represent p over p plus q, and phi to represent p plus q, and that actually lead to a brown new, version of a beta distribution. Now we don't have parameter p and q anymore, but we are having parameter mu and phi. So why do you think they did it? They did it because the phi, the mu, because if you want to actually model where you want to relate the outcome variable to some explanatory variable, you need mean equation. And that is why we want one of the parameters to be in terms of mu. That's why we are saying mu. Okay. Now, let me just tell you, even the conventional one, this guy here, okay, from statistical theory, okay, mean and variance is actually this. The expected value of y is mu equal to p over p plus q. The variance of y is what you are seeing right now. So, the Ferrari and the like in 2004, they actually, use the idea of the mean of the distribution in their reparameterization. Okay, now that I've walked you through beta distribution now, so which is an underlying distribution for beta regression. Now, what we want to do now, since Ferrari and the like, they've reparameterized, the distribution. So what we want to focus on now is focusing on mu and phi. Okay, now the mu is going to go from 0 to 1. Okay, and the phi is going to be greater than 0. Therefore, if I want to write, I'm going to say y follows a beta distribution with mu and phi, because the phi is basically going to act, the reciprocal of the phi is going to act as a dispersion parameter. If mu represents the mean of a model, we always need a dispersion like in form of a variance. You get what I mean? Okay, so if the expected value of y equal to mu, okay, if I have a response variable y lie between 0 and 1, then the variance of y right now in terms of mu and phi is going to be this guy. Okay, so I needed to take a look at all of that. Now the parameter phi is known as a precision parameter. Okay, I told you the mu is the mean of the response, while the phi now is the precision. How precise is my model? Okay, that is what's going to tell us that. So the phi is known as the precision parameter, like I said. And for a fixed mu, the larger phi, okay, the smaller the variance. Because when the precision is high, what do you expect from the variance? Because of that, I'm actually going to say, uh, you know, the precision and the variance, they are actually inversely related. Precision and the variance. You get what I mean? The more when you have a more precise, then it means a less variance. Does that make sense? When something is more precise, then that translates to less variance. Okay, now I need you to take a look at that. If y1, y2 up to yn is a random sample from a beta distribution, okay, with parameter mu and phi, okay, we can write a beta regression as that. I'm writing that in a matrix form. Okay, we can have a beta regression as that. Okay, now if I have a beta regression as that now, okay, just like what I said the other time, okay, the variance of yi in terms of mu and phi is this guy. What did I call mu? The mu is a mean function of the model. I'm calling the mu now S transpose beta. What do I mean by that? When I say S transpose beta, it's more or less like writing beta 1, x1, beta 2, x2, and so on. Does that make sense? That is what it means, S transpose beta. Okay, so we are equating, Of course, that is expected value of y given s, so which is equal to mu. Okay, this guy is what I'm actually calling that. Okay, take a look at that. Okay, and of course, if I actually have that as equation one, okay, then we can find the likelihood. The idea of what I'm doing in equation two is just for us to, if I take the likelihood of what was parameterized, this guy here, this one, the second one, I'm talking about this guy, okay, taking the likelihood of that, because we want to estimate parameters in that, and the method of maximum likelihood will be used. And so when I say my likelihood is just taking the joint density function of that, okay, so what we actually have in equation 2 that you can see. And don't forget, later we're going to plug in mu. Mu is going to be the mean function that we talk about. Okay, so this is just giving you the idea of what is behind the scene. Okay, so we have other extension of beta regression, but I'm not going to go into there. What I'm going to walk you through now is the application aspect. Now I need you to pay attention to the application aspect. Okay, so let's talk about the basic model. Let's talk about how do we estimate parameters, how do we conduct inference, and how do we actually subject our model to diagnostic testing. Let's take a look at this. The variable of interest is yield, and the yield is proportion of crude oil converted to gasoline after distillation and fractionation. Let me tell you, those that work in industrial chemistry, okay, that they actually trying to convert crude oil into gasoline. It is not 100% of the crude oil that will get converted into gasoline at the end of the day after distillation and fractionation. Out of 100%, how many of that gets converted? Okay, it means we're actually going to use the idea of a beta distribution, because of the fact that the response variable here is going to lie between 0 and 1. You get what I mean? Okay, so this is one of the example here. Okay, the proportion of crude oil, converted to gasoline after distillation and fractionation, okay, and for which I said a beta regression model is rather natural for that kind of phenomenon. Okay, so I said beta regression is commonly used when you want to model y that are probability themselves. Why are they probability? That is a range of the probability, 0 to 1, right? Okay, now, and I just talked about, we're going to make use of a gasoline yield data for as an example now. Okay, I want to take you into R now. I want to take you into how you basically you can implement beta regression in R. And I just walk you through what is it called? The theoretical aspect of that. But let's go into the apply. Okay, I want to use the gasoline yield data, which is a proportion of crude oil that get converted to gasoline after distillation and fractionation. Okay, that's one example. Another example is when you talk about the proportion of individuals infected with XYZ. Of course, I remember the other time during the COVID did not infect everybody in the world. It's only with due respect to those, that die due to COVID or get infected due to COVID. That's an example, because it did not affect 100% of people in the world. So that becomes a proportion of individual that get infected. Okay. Now I want to take you into how you can implement beta regression in R. If you want to do that, you need to load a package. You need to install a package called beta reg. Okay, beta reg. Okay. Now, the moment you load this beta reg, you install that and you actually load that with your library. Okay. Now you can actually, there are some data that are inbuilt in R. Okay, the gasoline yield data is one of them. So if you actually write data into BAT okay, with a package equal to beta reg, you're basically going to have access to the data. Okay, uh, if I now want to model this, you know what I'm going to do? Okay, it's going to be beta reg. Do you see beta? Do you see beta reg? The beta reg yield is a response variable. You know what I want to do here? I'm looking at the effect of batch and temperature on the yield because I know in the process of, we talk about the fractionation or the distillation where crude oil is being converted to gasoline. Of course, that's gonna come out in batches, right? We want to look at the role played by batches, and not only that, what about the effect of temperature? Of course, the temperature will actually be used, to in the distillation process. Okay, so you see beta reg, okay, yield on bash plus the temperature, the data I'm using is gasoline. Okay, when I do this summary, okay, I'm going to show you what is going to come out. Okay, so what is going to come out? I'm actually going to add this, and this is going to be the output in R. This is basically looking like the linear regression output that we've done before, except that I needed to look at the Z value. There's no, instead of the T value, you can see a Z value, right? Take a look at that. Okay, so the numbers of batches that was used, they used 10 batches. That was why arrow is reporting 9. Does that make sense? Don't forget the degree of freedom of when you have a categorical variable with the numbers of levels k. Okay, what arrow is going to report is k minus 1 is going to nested 1 in the intercept. So we have batch 1 to batch 9 or 5, 6, 7, yeah, 9 now, and the temperature. And when you take a look at the p-value, okay, when you take a look at the p-value of all of that, okay, the predators here are significant. When you compare the p-value with the 0.05, these are all less than 0.05. Like this same data, if you use other variants of logistic regression to actually implement this, you're basically going to mislead. Does that make sense? It is not as if our models are failing us. Our models are not failing us, but we are the one that we're not applying the right model. So when you apply an appropriate model to a given situation, begging, of course, we're basically going to have a way out. Okay, we normally encounter issue when we're always in a hurry and we don't, we ignore, uh, violations of assumptions, applying an inappropriate model. Okay, so take a look at that. Now, the next thing that I actually want to talk about, okay, do you know that when we're talking about when using beta regression, that doesn't mean everything is fine. You know why? Because what we normally encounter with a situation where the response variable is between 0 and 1 is a problem of heteroscedasticity. Has anybody heard about heteroscedasticity before? Whether in person or online, heteroscedasticity means non-constant variance. Non-constant variance. Okay, non-constant variance. That is what we call heteroscedasticity. Heteroscedasticity is a problem in modeling. Okay, you remember one of the assumptions of linear regression is actually constant variance, right? A constant variance means homoscedasticity. There's no problem with that. But the moment you have a non-constant variance, that is heteroscedasticity. And let me tell you, in a situation where the response variable is a rate, a proportion, okay, we don't expect a constant variance. We expect the variance of y to change given the value of predator. And this is what we can do. We can actually try to consider, using what I call a variable expansion model as a way out. So this is what I'm going to do. Even though, and that was why I said, although the beta model already incorporates naturally a certain pattern in the variances of the response, because what we did before in equation one, okay, if you take a look at equation one here, you see variance of y high, right? Y high. It means the variance of y1 will be different from variance of y2, will be different from, there's no constant variance here. Okay, so even though we've incorporated the fact that, okay, we're working with a situation where the response variable is not expected to have a constant variance, we still need to incorporate what I call variable expansion. And this is what we're going to do in the variable expansion. And that was why I said it might be necessary to incorporate further regressor to account for heteroscedasticity. Okay, and there's somebody who suggested that idea was Simas et al. 2010. The Simas et al. 2010 suggested the idea. You know what we're going to do? I need you to pay attention to what we want to do now. Initially we actually look at the effect of bash temperature on the yield. We add a result, but okay, the result is actually this. But there's always a way to see, to improve on our results. Okay, and if I incorporate a variable, in a variable that we account for heteroscedasticity, and if that variable, if effect of that variable turn out to be significant, then it means we need to do what we do. Now take a look at this. I needed to look at the code very, very well. Okay, I actually looking at the effect of bash and temperature. Do you see that vertical line, right? In the vertical line, I believe, okay, what could cause the problem of heteroscedasticity in the first place, it means what could make the variance not to be the same? It's going to be the temperature. Don't forget, in distillation, right? They adjust the temperature, they manipulate the temperature, right? Okay, and that was why I'm actually using temperature as a regressor to account for heteroscedasticity. Oh my God, look at the results. When you take a look at that, it is only that temperature and the intercept that will be plotted. When you take a look at the p-value now, what happened when that turned out to be significant? What that actually means. That signal a significant improvement, including a temperature regressor as a dispersion predator. Does that make sense? But if it is not significant, then we just need to rely on what we got before. Does that make sense? Okay, so that is what I mean by exactly what I did here. Okay, now another thing I'm going to talk about, another way we can look at it is, do you know we can use the idea of a likelihood ratio test where, take a look at this. We got two models. Look at the first one. In the first one, we fitted the conventional beta regression. Oh, give me 1 second. I'm actually, okay, I take a look at this guy. You see the first model? In the first model, I fitted conventional beta regression. I did not incorporate any other regressor to control for heteroscedasticity. Okay, why do you think my assumption is going to be for that? My assumption is that the model is equally dispersed. That is for model one. But do you know what model two is trying to say? Model two is trying to say they are not actually equally dispersed. You needed to further incorporate a temperature, a particular predator that will account for heteroscedasticity. In model one, you are trying to pretend as if there's no problem at all. And that was what I put it here. Know that this can also be interpreted as testing the non-hypothesis of equal dispersion against a specific alternative of variable dispersion. Okay. Now, when you take a look at the model one, where I'm looking at the effect of batch and temperature on the yield. Okay. But when we take a look at model two, I incorporate temperature to be able to adjust, which means I believe there's a problem with equal dispersion, and the temperature is what I can actually incorporate to adjust for heteroscedasticity. Okay, so when I do LR test, the likelihood ratio test, what happened in the end, I got a p-value that is less than 0.05. What does that mean? When the p-value is less than 0.05, then it means you're basically rejecting the non-hypothesis. The non-hypothesis here actually supports model one. Does that make sense? Why the alternative hypothesis supports model two. So here now we are rejecting model one, okay, believing that initially there was nothing like equal expansion, okay. We needed a temperature that we actually adjust for, the problem of the heteroscedasticity. Is there any question or any person online before I move on? Okay, those of you online, can you confirm again if you are still hearing me clearly? Can you
Yeah,
confirm
we
by talk?
can hear you.
Okay, thank you so much. And thank you for confirming that. Okay, so I'm going to erase that now. I'm going to go to the next slide. Okay, go ahead. Okay, quick question on the last slide. Okay. Oh, the 87 and 84, they are just log likelihood value. We're not going to make use of that. Okay, what actually led us to the p-value? You remember the other time we talked about g squared, which is the when you subtract the likelihood, the 84.8 is a likelihood value for model one, and 87.0 is a likelihood value for model two. But the chi-square, deviance is 4.36. So the p-value associated with that is what we need when we want to take a decision. And right now the p-value is 0.037. Does that make sense? But if you want to compare them by way of log likelihood value, of course, you're going to say model 2 has more log likelihood value, but we don't, that is not sufficient. That may be necessary, but the major thing in hypothesis testing is to make a conclusion using the p-value. Does that make sense? That's a very good question. Okay, so I want to go to another question. I want to leave industrial chemistry now. I want to go house food expenditure. Let's take a look at this now. It's going to be a very good example. So house food expenditure data for 38 households. The dependent variable is food divided by income. You know the meaning of that? It is not the total amount of money that you get that you spend on food. Okay? You're also going to pay for rent and so on like that. So food divided by income is going to be a proportion that lies between 0 and 1. Okay, so the proportion of household income spent on food, that can be more than 100% of your income. That's not possible. Okay, so two explanatory variables are available. We basically want to make a prediction of that. Okay, we talk about the previously mentioned household income and the number of persons in living in the household. That will depend. Like in my household now, I got 5 children. With my wife, we are 7 in number. Of course, we're going to spend a lot on food, but the amount we spend on food will not be more than my income because I'm also going to pay for rent, pay for insurance, so on like that. Okay, now we actually how do we have now? There's something I want to show you now. We have a standard test in statistics. If you basically want to conduct a test on heteroscedasticity, it is it is believed that if a response variable is between 0 and 1, naturally there will be problem of heteroscedasticity. It's going to be non-constant variance. We know that. Okay. Now, this is a test. Like there's a test called Brent-Spiegel test. Okay. Studentized Brent-Spiegel test is a test on heteroscedasticity to see whether it exists or not. Okay. If you load library LM test, then you're going to do BP test. Okay. The FE underscore LM is basically maybe I want to fit a linear regression. Okay. I'm just going to show you that. The p-value here is 0.051. That's too dicey. That's kind of close, right? Okay. But take a look at this. Let's say, for instance, somebody made a mistake by fitting linear regression to this data. You fit linear regression, you basically your response variable is a fraction, is a proportion, and you fit multiple linear regression. Okay, you're still going to have a result. This is fitting a linear regression now, fitting an ordinary least square. Let's see the results. Oh, this is the result. Even if you look at the income, the person is significant, and you're going to start celebrating. Don't celebrate yet. This is not an appropriate model. Somebody's going to argue this out. Why is it that this is not an appropriate model? The result is making sense. Income determine what I'm going to spend. The number of person living in my household is determine what I'm going to spend. But I'm going to tell you the reason why this is not appropriate. If somebody commit an offense in the state of Minnesota, can I ask you this question? Can the person be tried in the state of New York? No. Even if the state, let's say the person run to New York and the person is being tried using New York law, even if the New York was able to establish the fact that he committed the offense, whatever they decide will be declared null and void. You know why? Because New York does not have a territorial jurisdiction in law, to entertain the case. Because that person supposed to be tried in where he committed the offense. The same thing is applicable here, even though the linear regression is giving a promising result. Like the income is significant, the person is significant, but it is not appropriate. Okay, now in model 2, now, you know what I want to fit? I'm fitting beta regression. Okay, so fitting beta regression. But when you take a look at the model 2, okay, I'm fitting beta regression, and and I know that what will be violated using linear regression is going to be this guy here. That was why we're doing this. We're trying to conduct a Brent-Spiegel. When you conduct a Brent-Spiegel, the p-value is 0.0051. That's too close to call. Don't forget, the level of significance is 0.05. Okay, so at times the linear regressions are promising, but you know what? There's going to be violation of absorption. Okay, and because of that, okay, when we actually fit in the beta regression, we can actually have a way to solve the problem of the heteroscedasticity. Okay, because I know that is what they're going to argue out, because um, the, the 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 range of response variable outcome is 0 to 1. Okay, of course, naturally there will be problem of heteroscedasticity, but you know what? I'm incorporating person. Uh, Oh, okay. This one is when I've not incorporated person, and when I've not incorporated a expansion variable. As you can see, this is also stand out to be significant. Okay. Now this is a conventional beta regression model. Can you see that now? Okay. This is an appropriate model to fit. But even though I can still improve on this model by trying to go this way. What have I done now? Okay, actually using person. Do you see a vertical bar? Let me show you. Do you see this? Do you see that vertical bar? After vertical bar, you see persons, right? That was what we did the other time when we're trying to incorporate one of the predator that is likely to cause the problem of heteroscedasticity. It is it's just like somebody commit the offense, then the person should be punished. So we believe that number of persons in the household, okay, will actually play more significant role to causing the problem associated with the income, the amount of income spent on food. And that is the reason why we're actually putting that. Okay. And when we put that, we can conduct a likelihood ratio test to see between this one and the conventional one, where we are assuming equal expansion. Does that make sense? And what happened in the end? Well, oh my God, look at the p-value. Okay, look at the p-value. Then it means the second model, the model two, where you actually incorporate, okay, you know, a person as a variable, to adjust for the heteroscedasticity. As you can see now, the p-value is 0.0055, and that is less than 0.05. So which means this is fantastic. But do you know that you can also do another thing where I put persons now? You can also put income. When you put income, compare your result. Like use a likelihood ratio test to be able to see which one is better. Does that make sense? You can do your research too. Okay, now it is not only likelihood ratio test that we can actually use when we're comparing. We can also use the AIC. Okay, I told you the other time, the AIC. Okay, the one with the lowest AIC would be preferred. Okay, look at that, FE beta and FE beta 2. Okay, the FE beta. Okay, the FE beta is when I'm assuming equal expansion, when I did not, incorporate, any predator to adjust for heteroscedasticity. And the second one is when I incorporate. So if I want to get the AIC, I'm just going to write AIC into FA beta, comma FA beta 2. Okay. In the end, look at what I got. Which one has the smallest AIC is the second one. The smallest is the second one. And that was why I said, thought there is evidence for variable expansion, and module F underscore beta 2 seem to be preferable. Does that make sense? Okay. Now, the last thing I'm going to say before I go is what we call link. Oh, go ahead. Okay. Oh, the K, it means the that very K means what I'm actually doing is BIC. You remember the other time AIC, that place is going to be like 2K, right? But for BIC log of, yeah, that's a good question. So which is telling me I'm actually computing BIC. So AIC, BIC, they are module selection criteria that incorporate both module fitness and module complexity. That's a good question. Okay, do you know that we can also improve on the best module? As far as the world is concerned, there's no model that is the best. It is best right now. We see have a lot of professors working right now trying to improve on the model. You get what I mean? Okay. Now we may also want to improve on the link function. Okay, as proposed, by MC Collag and Neda in 1989. Okay, and I needed to pay attention now. Okay, you know, in a situation when you take a look at what I'm actually displaying, when you look at the first one, okay, the link function is more or less like an identity. But when you take a look at the second one, I'm using a log. What is it? What is the meaning of log? That's a transformation, right? Okay, why are we transforming? Because there's a problem with a response variable in the 0, 1. Okay. Now one can decide to say, okay, can we have an improvement on what we have by indicating a log, okay, or using the conventional one, okay? When I look at here, we're going to look at the pseudo house squared. We call it pseudo R squared. The one that have the most pseudo R squared is the one that will be preferred. Take a look at the one with the log, that's 0.98523. Why the one without log, where we use an identity, the conventional one, actually has 0.96173. So which means the log one should be preferred. Now take a look at this one now. You know, between the log. Now, when something is log, and at the same time, you actually incorporate a variable, okay, that we account for the expansion. Take a look at the first one. In the first one, the GY underscore logit, that's just a conventional beta regression model, okay, using identity link function, link identity, okay, and there is no, we are zooming equal expansion, there's no predictor variable that we use to adjust. But take a look at the second one, GY uh, underscore logit 2. What happened? Temperature is being used to adjust for heteroscedasticity. We're still using identity link function, but look at the GY underscore log. In the GY underscore log, we did not use any variable, to adjust for heteroscedasticity. The only thing that we did is just to change the link from identity to the log. And let's see what happened. We can, how many modules do we have now? We got 3 modules, right? We can know which one is the best among them by writing the AIC. When I write AIC, I'm going to put 3 things because 3 modules. Take a look at that. Oh my God. Which one has the lowest AIC? Can somebody see on the board? Which one has the lowest AIC? The last one, negative 168.31, which means the length, when you get the length function right in a model, then you can improve the quality of your model. Take a look at that now. So which means the length function with the log is actually going to be the most preferred. This is where I'm actually going to stop today. Is there any question before I go today? Oh, those of you online, anybody want to ask question before I go today? Can you see hear me? Those of you online, can you see hear me?
Yes.
So the next day, what we're gonna do on Monday, the material is for this week. Because of the holiday, is Poisson regression. So the story of regression type continue. So what we're gonna do in Poisson regression is when the outcome variable is now a count. Okay, count. Okay, the number of customers that will visit my restaurant. What determine that? Situation where your response is count, no longer continuous, no longer categorical, no longer in the 0 and 1. We're going to use Poisson regression. That's what we're going to do on Monday. But today, okay, we actually handle response variable in the 0, 1. You may want to talk about click rates, like in advertising on your website, okay? And you want to consider what determines click rates, okay, in your website. That will depend on size and position. Okay, there are a lot of variables. The click rate, is it everybody that actually when your website pop up, it's not everybody that will click that, right? Okay, the customers need to click on your website before they have to go through what you have in display before they can even buy. Okay, but one of us talk about the click rate. That's we actually can be modeled by beta regression. Basically want to look at what are the want to look effect of some factors that affect the click rate. Okay, this way I'm going to stop today. Is the end of the week. Make sure you all stay safe and have a lovely day. Bye for now, everyone.
Thank you.
You're welcome.